Good morning, ladies and gentlemen. I'm He from the School of Big Data and Software of Chongqing University. I'm honored and proud to have the opportunity to speak at this meeting. The title of my paper is Semi-Automatic Segmentation of Tissue Regions in Digital Histopathological Image. The subject comes from the project on the grading of cervical neoplasia in cooperation with the Department of Pathology of Xinqiao Hospital, affiliated to the Army Medical University. My report is divided into four parts: the background and the significance of research topic, propose solutions to problems and implement them, experimental results of the method, summarize and prospect. Next, I will explain each part in turns. The first part is the background of the subject, related work, research content, and significance. The incidence rate and the mortality rate of cancer in China is the world's first. Pathological examination has been regarded as the gold standard for cancer detection and diagnosis. Different local areas of pathological images are closely related to the cause and severity of the disease. However, the traditional manual segmentation method is limited by time-consuming, unstable, strong subjectivity, and high error rate due to visual fatigue. Developing an intelligent automatic algorithm to efficiently segment different tissue is crucial for the development of pathology-assisted diagnosis. It can be learned from literature research that dataset, segmentation accuracy, and model portability are still the difficulties in tissue segmentation. In addition, most deep learning methods are lack of explainability and has no acceptance in the medical industry. Therefore, this paper is to design an algorithm to automatically identify and segment various tissue regions in pathological images and determine their tissue types. The significance of this topic is to improve diagnostic efficiency, provide a general segmentation scheme, and reduce reliance on public data sets. The second part is the core of our paper. A semi-automatic segmentation model is proposed for tissue segmentation. This figure shows the flow of the semi-automatic segmentation model. Firstly, the pathological images conduct staining normalization, and then the pre-segmentation of tissues is realized on the processed images based on superpixel classification. Then, the deep learning model is trained for automatic segmentation based on the results of pre-segmentation of tissues and labeled data. The semi-automatic segmentation model of tissues is divided into two stages: pre-segmentation and automatic segmentation. Due to the lack of tissue label, deep learning cannot be directly used for training segmentation model, so we start with the accurate division of tissue boundaries. Superpixel is a series of pixels that are adjacent to each other and have similar color, brightness, texture into small regions. It can better preserve the tissue boundary. Superpixel classification can realize the preliminary segmentation of tissue with no labeling cost. It is divided into three steps: image pre-processing, data production, tissue region pre-segmentation. Based on the presentation derived from color deconvolution, the nonlinear mapping from the source image to the template image is found, and the staining normalization is realized. In the figure, the left is the target image, the middle are source images with shallow staining and deep staining, and the right is the staining normalization result corresponding to the source image. In this paper, SLIC method is used for superpixel segmentation of different scales. The multi-scale facilitates the model to reconcile the labeling cost and the segmentation effect. Superpixel labeling is done by people trained in basic pathology. The probability that each superpixel rectangular belongs to a specific tissue is determined. Superpixels are rectangularized to be able to feed them into the CNN for classification. The external rectangle of the superpixel is obtained by topologically analyzing the superpixel mask. Table 1 shows the correspondence between the number of superpixels and the size of superpixels in a picture. Superpixel labeling can be quickly completed by inexact supervision. The label of each superpixel is probability, as shown in the formula. In addition, data enhancement operations are performed on the labeled superpixels. Cervical histopathological image dataset provided and authorized by the hospital. All personal information is withheld to protect patient privacy. Details of the pre-segmented dataset are shown in the table. CNN is constructed to train the superpixel classification model. The network structure is shown in the figure. The rectangular superpixels are used as the input, and the category probability marked by doctors is used as the label. Superpixel classification is evaluated by mean cross entropy loss and accuracy. The superpixel classification results are reorganized into tissue segmentation results according to the division rules and the categories. Considering that the superpixel classification in the pre-segmentation process involves complex processes such as superpixel division and the rectangle, and the whole pathological image is divided into superpixels for independent classification, ignoring the association between superpixels. For example, superpixels with similar positions are likely to belong to the same organization. Therefore, in order to consider the integrity of the pathological image and obtain some tissue segmentation labels, we can use the deep learning technology to directly learn the whole pathological image and complete the automatic tissue segmentation. Automatic segmentation includes dataset labeling and the automatic segmentation of pathological image tissue region. The automatic segmentation dataset is constructed based on the pre-segmentation results. The dataset consists of 1,662 staining normalized images and the corresponding tissue masks. Use structure of the UNet enable learning of both high-level and low-level features. An improved UNet architecture for replacing the VGGNet with the first 4 layers of the ResNet 50 is used to avoid gradient disappearance for deep network training and improve the model segmentation accuracy, which is called UNet plus ResNet 50 in this paper. The methods widely used in image segmentation are selected for comparison with our method, including SVM, RBF, Random Forest, FCN, and UNet. Accuracy and the mean IOU are as evaluation metrics of models. The third part is the experimental results and the analysis. The classification of the superpixels is shown in Table 3, where epochs is the number of training runs and batch size is the batch size of each input data during training. It is clear that at epochs of 24 and batch size of 20, mean loss and accuracy are iterated to optimal, achieving 85% classification accuracy. Experiments also verify the effect of different size of superpixels. As shown in Table 4, the classification model achieved more accurate results when the superpixel size is 128. That is, each pathological image is divided into 50 superpixels. The left is the original image and the right is the pre-segmentation results of tissue region. However, for images with more complex staining distribution and more disordered cell arrangement, the pre-segmentation model has a greater error. Table 5 shows the accuracy and the mean IOU of the 5 models for segmenting the tissues. SVM, RBF, and the random forest are not due to the limitations in nonlinear mapping capabilities and the parameter estimation. FCN is able to utilize information from multiple layers simultaneously, but it is not sensitive to details and lacks spatial consistency. The baseline network unit is more accurate than the above methods. However, UNet usually needs random initialization and has many parameters. Compared to other deep learning models, the improved UNet plus ResNet 50 achieved better segmentation results, and each image can be segmented in less than 1 second, which satisfies the need for fast segmentation. The intuitive segmentation of each model is shown in Figure 8. The red outline is epithelial tissue, the white area is the background, and the rest is fibrous tissue. The results of pre-segmentation and automatic segmentation of epithelial tissue are visually compared as shown in Figure 9. The automatic segmentation model, based on deep learning, learns the unique cell arrangement patterns and the specific pathological features of the epithelial tissue, and thus performs well even on cervical pathology images with disordered cell alignment and uneven staining. To further validate the generality of semi-automatic segmentation model, it is also used to segment glandular cavity tissues in cervical pathology images. The visual display of the segmentation results is shown in Figure 10, which achieves medically acceptable results. This further demonstrates that the semi-automatic segmentation model provides a versatile solution to segmentation lesion regions in various tumor images. The fourth part is the summary and the discussion. The innovation of this paper lies in, first, improve model accuracy and interpretability and through key interactions with pathologists. Second, superpixel level labeling replaces the traditional pixel level labeling, retains the organization boundary, and the inaccurate supervised learning method greatly improves the labeling efficiency. Third, the semi-automatic segmentation model has strong universality and can be applied to the segmentation of a variety of cancerous pathological images. Although the semi-automatic segmentation model provides a solution for rapid and accurate segmentation of tissue regions in various pathological sections, there are still some problems worth studying. Number 1, reinforcement learning is used for superpixel classification. Number 2, tissue segmentation combined with more types of stained images of pathological tissues. Number 3, expand the research content of pathological images which is no longer limited to tissue region segmentation, cell segmentation, morphological analysis, tissue structure and localization can further assist computer diagnosis. These are all the contents of my presentation. Thank you.